Welcome to this training on analyzing and designing robust AI data center architectures. In this session, we will explore the critical components, network topologies, and technologies required to support high-performance AI workloads. To begin, we must recognize that the traditional data center model is evolving. We are seeing a divergence into two distinct classes, AI factories and AI clouds. An AI factory is purpose-built for training massive models, like large language models, requiring thousands of GPUs to act as a single supercomputer. Conversely, AI clouds extend traditional cloud infrastructure to support generative AI applications, handling diverse workloads from thousands of users. Understanding this distinction is the first step in design, as it dictates your networking choice, whether you need the raw, unified power of an AI factory or the flexibility and isolation of an AI cloud. So what did we learn? We learned that defining your workload type training versus inference and single versus multi-tenant is the foundational step in architectural design. Let's visualize this decision process. We start with the workload demand at the top. This flows into our decision point, architecture type. If your goal is massive model training, you branch to the AI factory node, which focuses on maximizing throughput, essentially ensuring all GPUs work continuously. If your goal is serving diverse users, you branch to AI cloud, where the focus shifts to maximizing performance isolation and flexibility. Both paths ultimately converge on unified compute, meaning, regardless of the path, the underlying infrastructure must support accelerated computing. Designing for AI means solving for distributed computing. Unlike standard web traffic, AI workloads generate elephant flows, massive bursts of data moving between GPUs. In this environment, the entire cluster is only as fast as its slowest node, a concept known as tail latency. If one packet drops or one link congests, hundreds of GPUs stall, waiting for data. Therefore, your architecture must prioritize a lossless network fabric. You cannot rely on traditional statistical multiplexing. You need deterministic performance to ensure that training jobs complete on time. So what is the takeaway? We learned that in AI architectures, minimizing tail latency and packet loss is critical because network delays directly translate to wasted GPU cycles and money. This diagram illustrates the impact of network issues. GPU A sends a massive elephant flow of gradient data through the network to GPU B. Notice the cross mark on the network line. This represents congestion or packet loss. Consequently, GPU B enters a wait state, sitting idle while it anticipates data. GPU A must then retransmit, causing the data to arrive late. The note at the bottom highlights the result. Training stalled. This visualizes exactly why a robust architecture must eliminate these drops to maintain continuous computation. For AI factories, NVIDIA Quantum InfiniBand is the gold standard. It is designed inherently for high-performance computing. A key feature here is in-network computing, specifically the scalable hierarchical aggregation and reduction protocol, or SHARP. Instead of sending data back and forth between endpoints to calculate averages or reductions, the switch hardware itself performs these calculations as data traverses the network. This effectively doubles the data bandwidth available for these operations. Combined with self-healing capabilities and adaptive routing that dynamically bypasses congestion, InfiniBand ensures maximum efficiency. What did we learn? We learned that InfiniBand isn't just moving data, it's actively processing it via SHARP to reduce the load on endpoints. While InfiniBand rules a factory, Ethernet is evolving for the AI cloud. NVIDIA Spectrum-X platform transforms standard Ethernet into an AI-ready fabric. It introduces adaptive routing on top of ROC, which sprays packets across all available paths to prevent hotspots, rather than sticking to a single flow path like traditional Ethernet. Crucially, it provides performance isolation. In a multi-tenant cloud, one user's heavy workload should anti-degrade another's. Spectrum-X ensures that noisy neighbors are contained, providing predictable performance for everyone. So the important point here is that Spectrum-X allows you to leverage the ubiquity of Ethernet while achieving the lossless, high-bandwidth performance required for AI workloads. This class diagram contrasts the two Ethernet approaches. On the left, we have Spectrum-X platform with attributes like packet spraying and congestion control. On the right is traditional Ethernet, relying on static hashing. Both interact with the AI workload class in the center. The connection from Spectrum-X shows it is optimized for these workloads, while the dotted line from traditional Ethernet identifies it as a bottleneck. This visually confirms why specialized Ethernet is necessary for modern AI. Now let's look at the physical topology. For large clusters like the DGX SuperPOD, we use a rail-optimized design. Deep learning training requires massive synchronization between GPUs. In this design, we don't just plug cables randomly. We connect the first HCA of every node to the first leaf switch, the second HCA to the second leaf switch, and so on. This creates parallel rails of connectivity. This structure ensures that when GPUs need to synchronize, they communicate over the shortest possible path, often passing through only a single switch. What have we learned? We learned that physical cabling strategy, specifically rail optimization, is a critical design element that directly impacts the speed of collective operations like all reduce. This graph visualizes the rail concept. Look at rail 1 on the top. HCA1 from node 1 and HCA1 from node 2 both connect directly to leaf switch 1. Similarly, in rail 2 below, the second HCAS connect to leaf switch 2. This creates dedicated parallel lanes for traffic. Both rails eventually connect to the spine switch for cross-rail traffic, but the primary synchronization traffic stays within these efficient single-switch rails. Hardware acceleration isn't limited to the switch. We deploy NVIDIA BlueField-13 DPUs and Super NICs at the server edge. The DPU acts as a computer in front of a computer, offloading infrastructure tasks like storage virtualization, security policies, and telemetry from the main CPU. This creates a zero-trust environment where the tenant workload is fully isolated from the infrastructure control plane. For AI clouds, the Super NIC works in tandem with Spectrum-4 switches to enforce granular congestion control at the edge, ensuring data flows smoothly. What is the key takeaway? We learned that DPUs and Super NICs are essential for securing the data center and preserving expensive compute resources for the actual AI workload. In this component diagram, we see the server node structure. The host CPU runs the workload, but notice that the traffic flows down to the BlueField DPU. The DPU handles infra services and connects to the network fabric. The note emphasizes that the DPU is offloading security or storage. This visual separation illustrates how the DPU insulates the host CPU from network overhead and security checks. A robust architecture requires robust operations. You cannot fix what you cannot see. For InfiniBand, we use the Unified Fabric Manager UFM to monitor fabric health, manage congestion, and perform preventative maintenance. For Ethernet, NVIDIA NetQ provides real-time visibility. A standout feature across both is what just happened, WJH. Instead of generic error counters, WJH provides detailed, ASIC-level data on exactly why and where a packet was dropped, whether due to buffer exhaustion, ACLS, or signal integrity. So what did we learn? We learned that granular telemetry, like WJH, is mandatory for reducing mean time to resolution in complex, high-speed AI networks. This chart breaks down the critical components of AI network visibility. The largest slice, WJH events, represents 40% of the insight, focusing on drops and latency anomalies. Flow telemetry takes up 25%, helping track application performance. Config validation and link health make up the remainder. This highlights that while link status is important, understanding dynamic packet behavior via WJH is the most significant factor in troubleshooting AI networks. Finally, we ensure robustness through validation. Before deploying physical hardware, we use NVIDIA Air to create a digital twin of the data center. This is a bit-accurate simulation of the network control plane. It allows architects to validate routing policies, automation scripts, and security configurations in a risk-free environment. By treating infrastructure as code and testing it on a digital twin, you eliminate configuration errors before they touch production. To conclude this session, the most important point to remember is that robust AI architectures are not just built. They are simulated, validated, and continuously monitored to ensure they can deliver the immense scale required by modern AI. This final workflow diagram shows the validation lifecycle. We start by defining topology, then move to NVIDIA Air Sim to deploy the digital twin. From there, we enter validate config where we run automated tests. If they pass, we move to production deploy. If they fail, the arrow loops back to the start, allowing us to iterate safely. This circular feedback loop is the essence of a robust, risk-averse design process.